Okay, we move forward to the page 3.11. Now I give you the definition for different kinds of average diameter used for different purpose. The definition basically coming from these equations. We say djk, jk, the index represent different kinds of the average measure you may use, j corresponding to j in the order j minus k here. And you can have two representation here. For example, in the middle, this the equal definition, they tell you the integration where from the minimal droplet size to the maximal droplet size. Actually, this equation basically corresponding to real measurement, because when you do the measurement, you may have a droplet the limitation for your instrumentation. You cannot measure too small droplets in your spray region. For example, there is maybe have some kinds of nano particles inside of the spray field, and by using the regular the laser diagnostics, you may not have cannot measure too small droplets. Then there is some limitation. Then for realistic measurements, then the calculation we're starting from the minimal droplet size to the maximum. Okay. And here the representation inside of the integration, there you dj times dn divided by dn dt. dn dt, as we defined earlier, is equal to f of d, right? This is a distribution function. Okay, we have like this curve, the continuous variation curve. And a dj, okay, j, if j equal to 1, actually they are talking about the average, the total value you can evaluate based on the droplet diameter is only, and you use the d square, not a d square, I'm sorry, t to the 2, to the power of 2. That means that you are calculate the surface of your droplets, then you try to figure out the total surface area you may have from the liquid drop. And you go to the third order, then you are calculating the total volume by this minimum. And here they tell you that we use the two index for the comparison. For example, I give you the wait a second. Maybe we go to the next one. Well, the next one, actually, they are almost the same, right? The integrate the forms in the integrations, actually they show the same. The dt represented by f of t based on our definitions, but the integration, the upper and the lower limit, they will extend to the infinity to the zero. Actually, this is useful for the so-called theoretical calculation or numerical calculation. You can calculate to the droplet to the very large, right, to the infinity. Therefore, distance represent some theoretical conditions. You consider the all size of the droplet from 0 to infinity. Not the 0 is slightly a little bit larger than 0. Okay, but in reality, you should refer to the minimal droplet size to the maximal droplet size. Okay. Now we try to give you some example to understand this definition of for the average value for different kinds of purpose. Okay, the first one you think about D10. What is the meaning of D10? J equal to 1, then K equal to 0. What is the meaning of the K equal to 0? Actually, for example, if you look at the denominator, they just simply tell you, they just calculate the total number you have, right? This is a total number of droplets you may have. But the denominator represents you calculate the total diameters of your droplets. You use total droplet size divided by total number, then simply so-called the T10 represent the average, or we call arithmetic droplet diameter. Okay, it just give you the average value for the droplet size for all the droplets. Okay, now you change to D20. D20 then Z equal to 2, actually the denominator actually you calculate the total surface volume, total surface area of your droplet divided by total number. That means that you will have the average surface area. Let's say the diameter of a droplet whose surface area times the total number of droplet equal to the total area of the spray, which means that D20 represents the characteristic coming from the thinking the surface area distributions. Then simply you can see D30, they tell you the volume average. The D20 is the surface area average diameter, but this one is the volume average diameter. We call this as a mass median diameter. Sometimes you will use a so-called the MMD. The most important for combustion application, we use the so-called D32. D32 means you calculate here Z equal to 3. Z equal to 3 means you calculate the total volume of your droplet, right? And K equal to 2, they actually you calculate the total surface area of your droplet you may have. Total volume divided by total area, surface area, actually you will have an average diameter, right? Then this average diameter will represent two important characteristics together. The denominator represents the total volume you may have. For combustion, actually, we think about how much heat we can release from the chemical reaction, right? Then you are care about how much mass will participate in the chemical reaction, and then those mass through the chemical reaction will release heat, and the volume will represent how much mass you have. Actually, in the denominator, the physical meaning is we are considering those kinds of liquid fuel, how much heat can be released in the combustion process. Okay, this is one thing. The denominator, the total surface of area. Surface area represents how much vapor you can evaporate through the droplet surface, right? If you have a large surface area, you can promote the gasification strength, and this gasification strength be enhanced. Then later on, the mixing will be enhanced. The combustion efficiency will be enhanced. Therefore, surface area represents the other mechanism to think about is this spray is efficiently converts the liquid phase into the gas phase and mix well with air for further combustion process. Okay, the numerator represents how much heat you may release from the spray. The denominator represents how efficient the fuel can supply to react with air from the oxygen inside air. Then when you combine this together, actually D32, they simultaneously give you the influence coming from the total heat release and also from the impact efficient transport from the gasification process. Then people use D32 to identify suitable conditions for spray combustion. And here people use the shorter mean diameter. We call this as a SMD. Okay, and since by this definition, you will find out people use this formula and use it to study those kinds of influence on the practical applications. And I mentioned D32, so mean diameter, basically used for the combustion. But some people, if you just think about the evaporation, actually D20 will be a good one to indicate the impact on the purely gasification. For example, for the painting or for the some kinds of the humidifier, they may think about D20 is a good average diameter for use to categorize their behavior on their applications. Okay, which means if you have an injector, for this example, they will impinge out, and there is a droplet size distribution from very large. For example, when you do the measurement, the maximum droplet size they find is 360 micron, and the minimum one is just 10 micron. Then the distribution they find out use the old method to do the measurement. They find out from the 200 to the 360 micron, they have 100 droplets exist, and you have 1,000, 10,000, and it exists in different interval of droplet size. By doing the averaging or integration calculations, you will find out for this set of spreads, you may have the saw mean diameter here is around this value, around between maybe it's around 16 or 17, somewhere here. And you just think about the mass median diameter MMD, the average value may shift to the larger droplet size here. Okay, then the average value for different definition will give you the different physical meaning to apply to catalyze your physical characteristic of a spray in your application. For the combustion process, I mentioned again, we use the D3 as the average value to identify the droplet size in different positions of the spray field. Droplet size is one of the important character to be shown for the spray characteristic. The second one is also very important for spray characteristics. We call this as a so-called penetration. Penetration means how far your spray will penetrate through. This is very important, as I described earlier. If you have a high penetration through flange, that means that you will provide the droplets move for a longer distance. And this is especially important for industry furnace because the furnace chamber, the combustion chamber is long. You hope to understand how long the droplet can penetrate. That means that you will bring the flame to extend to a further distance. Okay. Sorry, I moved to the penetration test. I am sorry. Here, H. I just said the penetration, but yeah, I'm misreading. Actually, the second one is the patination. I'm sorry about it. But we go back to the patination. Patination basically tell you the distribution on the cross section of your spray. Okay, they say you the patination definition based on the uniformity of the circumferential distribution of fuel in a cone spray is generally referred to as is the so-called patination. Patination means that you take a cross section and to see the droplet distribution on that cross section of the spray. Okay, usually if you have a very uniform droplet size distribution, you can see the whole cross section contains different kinds of droplet, but uniform distributes. Okay, but sometimes you will have some poor patination. Poor patination means in these cross sections you may have certain area there is the pocket without droplets. Okay, and there is a pocket that has so many droplets exist. They have become dense. If you in this cross section you have a dense region, you have a dilute region, then you will have a trouble because in the dense region you may produce more fuel vapor, but less oxygen because they do not have enough room to mix together. But for the dilute spray regions, in this region, actually, you do not have too much fuel vapor, but you have some oxygen coming in. Based on the combustion consideration, you will find out in this portion, you may have a rich burning. In that portion, you may have a dim burning. Actually, the whole burning structure is not well distributed. Then somewhere you will have a richer, somewhere you will have a thinner. Then this is another good design for a stable spray burning. Therefore, patination is one of the important characteristics that you need to identify for your spray generated by the design injectors. Okay, this is a patination. I'm sorry, I jumped too fast to the penetration length, but patination, this is the definition you should understand. The third one, cone angle. Cone angle actually is another important characteristic. They will have a strong influence on ignition and stabilization limit, and also the exhaust smoke. Okay, usually a solid cone, okay, compared with the hollow cone. Solid cone usually you inject the spray out by the high pressure and push the liquid jet out. Then the liquid jet has very strong axial momentum. They will move more forward to the axial directions. In this sense, the cone angle usually is small, and this is typical application for so-called plane orifice atomizer. Then the spray actually they were influenced by the injection velocity only. If you have a strong larger injection velocity, then they will impinge to a far distance. They do not have enough radial momentum to expand their spray angle. Okay, in this sense, you will find out those spray actually is more so-called dense sprays. They do not have a chance to have a good mixing in the short distance of the spray. Okay. But for the hollow cone wide angle, for example, the swirl atomizer, as I described the simplex nozzle, since for the simplex nozzle, we apply the swirling into your liquid jet. Those swirling effect will give you the circumferential force to push your liquid to move radial upward. This kinds of radial motion will open your spray angle. Okay, when they open your spray angle, actually the momentum will be reduced along the axial direction, but increase along the radial momentum. Then the penetration depth becomes smaller, but they will move easier to the radial direction. Spray angle will be open. Okay. Then this distribution is dedicated by the aerodynamics of surrounding air in the primary zone. That means that they will have strong interaction with the outer air. Okay. This is two different types. For the hollow cone, usually they have a small angle, cone angle, then but they can they can impinge it to a further distance. But for hollow cone, because they were open with the wide spray angles, then they will reduce their axial momentum. The spray will be the penetration depth will become smaller. Okay, but they will have a good mixing with the air from the outer surrounding. Okay. Now, this is the droplet diameter is the first one you need to understand patternation. Second one, cone angle is the third one. Fourth one, we consider the so-called dissipation. Dissipation, the definition of dissipation is we try to compare the spray control volume with the liquid control volume. As I explained earlier, for a spray, and when you have a spray coming in, the whole spray cone we consider as the so-called the volume of the spray. Okay, the volume of spray. But inside of the volume of the spray volume, they have some droplet, and also they have some gas phase. Okay, and if you calculate the total volume of liquid, you may have bring this liquid volume compare with the spray volume. Okay, here they say the ratio. The dissipation means the ratio of the volume, the spray volume, compared with the fuel volume. Spray volume contains the fuel and the air. Okay, but fuel volume is just considered all the liquids together. And you simply say that you can see if the dispersion is very large. If you have a large dispersion means spray volume is much larger than fuel volume. Simply think about you have a spray volume, right? But fuel volume just a small. That means that in this volume, you do not have too many droplets exist. Then in this case, you just refer to so-called the dilute spread, right? Dilute spread. Dilute spread means that in the spray field, you do not have too much droplet exist. Okay. But if you have a smaller dispersion means the fuel volume is very close to the spray volume. That means that in this spray volume, you contain so many fuel droplets. Okay, almost contains all the region of your spray. Okay, then we call this as a dense spray. Easier to think about as I described when you have a spray jet coming out from the injectors. In the vicinity of injector, actually for the spray volume is small, and all in the spray region contains so many droplet size, droplet in, then the dispersion is very small. In this region, we call this is a dense region. But when you move away from the vicinity of the injectors to the very downstream sites, in this region, because spray cone extended, right? Spray extended, expand their spray region. The spray region, spray volume become large, and the droplet size, droplets become less. Then the dispersion become large. Then they tell you we are going to the dilute region. Dilute region, that means a good dispersion is good for fuel mixed rapidly with the surrounding gas, and the subsequent rate of evaporation and heat release are high, which means a good dissipation means the degree of dispersion should be small, and good for mixing and further for the combustion process. Final consideration, you need to think about the penetration as I described. Penetration means mainly tell you the spray may go to the maximal distance reach, and they will finish all the combustion at the end of the penetration test. Okay, and definitely how far you can go depends on the kinetic energy, the actual momentum of an inject fuel, initial jet fuels you may have, and the other one is a resistance coming from the accompanying air dynamic resistance of surrounding gas. Okay, in general, if we conclude the behavior for the different spray, usually there is a typical group of spray. One spray is you have a strong axial momentum. If you have a strong axial momentum compared with the radial momentum, usually the spray will move to a far distance. That means that you have a compact nano spray. In this sense, you have a small spray angle, but they can have a have a larger axial momentum to extend your spray to a longer distance. Then they will have a higher penetrations. But the other group is the so-called well atomizing, because we want to produce a large amount of small droplet size. Then you need to use you need to use the different kinds of mechanisms to increase the spray angles. Then you will have a high cone angles, and they will produce more entrainment into your spray cone to mix well with a tiny droplet. And since those tiny droplets will lose their momentum easily, then they cannot move to a far distance. The penetration depth will smaller. Okay. So here, for atomized spray of high angles, usually incurs more air resistance, then will tend to have a low penetrations. This is a typical two distinct characteristics for compact nano spray compared with the well atomized spray. Therefore, you understand why we need to use the micro explosion behavior for the multi-component droplet, because usually you need to think about, I'd like to have a spray that can extend to a long distance. But the next one, the consideration is you try to think about, I hope the spray will produce the so tiny droplets, but in this sense, the penetration will become smaller. Okay. Now, these two considerations actually they cannot compensate, except you can use the micro explosion. You use large droplet initially, and we wish they can has a longer penetrations, but at the certain main combustion regions, they will automatically break up to the so many tiny droplets by micro explosion. Then both advantage from the two consideration will reach together for your application on heating process. Okay, but anyway, there is some characteristics need to be used to check the spray behavior, and later on you can understand how to apply this spray into your spray combustion field. Okay, up to now I just try to give you some understanding. We always use the spray for different kinds of applications, but since the spray basically they give you the Yeah, they cannot give you the simple physical characteristic to identify its feature, right? Then you need to identify with the different kinds of characters to identify it. And we remember these several important factors you need to consider: penetration, dispersion, cone angle, and also patternation. And the most important thing is the droplet size evaluation you need to run. Then we close the spread atomization. Then we will move to the combustion to think about the combustion frame. Before we go to it, I will give you the experimental results on the droplet size evaluation on a specific simplex nozzle, and this will be discussed later.